Langchain Postgres Chat message histories. Description: this component allows you to store and retrieve chat message histories from a PostgreSQL database. This is useful for maintaining conversational context across multiple interactions and building applications that require persistent memory. Inputs: chat history, a list of chat messages. Each message is represented as a dictionary with the following keys: role, the role of the message; sender, e.g., user; assistant; content, the message content; databasery, the connection string for the PostgreSQL database; table name, the name of the table in the database where the chat histories will be stored. Outputs: storage historied, the unique identifier assigned to the stored chat history; retrieved chat history, the list of chat messages retrieved from the database. Steps: create a connection to the PostgreSQL database using the provided database URI. Insert the chat messages into the specified table. Retrieve the chat messages from the table based on a provided identifier or other criteria. Metrics: storage time, the time taken to store the chat history in the database. Retrieval time, the time taken to retrieve the chat history from the database. Number of messages stored, the total number of messages stored in the database. Visualization plots: chat history timeline, a visualization showing the timestamp and content of each message in pay. Chat history. Message distribution, a plot showing the distribution of message types, e.g., user messages, assistant messages in the chat history. Fine-tune parameters. Table schema, the structure of the table used for storing chat histories. Indexing strategy, the indices defined on the table to optimize retrieval performance. Uncertainty methods. None. Challenges and fixes. Challenge 1: data integrity, ensuring that chat message data is stored correctly and consistently. Sample use case that resulted in challenge 1: an incomplete message was stored due to network interruption. Fixes to challenge 1: implement error handling mechanisms to detect and correct data inconsistencies. Use appropriate data types and validation rules to prevent incorrect data entries. Challenge 2: performance optimizing, the speed of storing and retrieving chat histories. Sample use case that resulted in challenge 2: the system experienced slow response times during high usage. Fixes to challenge 2: employ database optimization such as indexing, query optimization, and database caching. Consider using a database connection pool to minimize connection overhead. Challenge 3: scalability, handling large volumes of chat histories efficiently. Sample use case that resulted in challenge 3: the database became overloaded when storing a large number of chat histories. Fixes to challenge 3: partition the data based on time or other criteria to distribute the load across multiple tables. Implement sharding to distribute data across multiple database instances. Challenge 4: security, protecting chat history data from unauthorized access. Sample use case that resulted in challenge 4: sensitive information in chat histories was compromised due to a security breach. Fixes to challenge 4: secure database access by using strong passwords and encryption. Implement role-based access control to restrict access to authorized users. Langchain Postgres Chat message histories. Postgres Chat message history. Description: the Postgres Chat message history class is a Langchain component that stores chat message history in a PostgreSQL database. This allows for persistent storage of conversations, enabling features like context retrieval across sessions and the ability to train conversational agents on past interactions. Inputs: connection string, a string representing the connection information for the PostgreSQL database. This typically includes the database host, port, username, password, and database name. Table name: a string specifying the name of the table in the PostgreSQL database where the chat message history will be stored. Outputs: chat history, a list of chat message objects. Each object represents a message exchanged during a conversation. The structure of the message object can vary but typically includes information like the message content, sender, and timestamp. Steps: establish a connection to the PostgreSQL database using the provided connection string. If the specified table name doesn't exist, create a new table with appropriate columns for storing chat message data, e.g. message content, sender, timestamp. When adding new messages to the history, insert them into the corresponding table row. To retrieve chat history, query the specified table based on the provided criteria, e.g. specific conversation ID, time range, metrics. Query execution time: this metric measures the time taken to execute SQL queries for adding or retrieving chat history data from the PostgreSQL database. Data insertion rate: this metric measures the number of chat messages that can be inserted into the database per unit time. Visualization plots. Conversation timeline: a visual representation of the chat messages over time, showing the flow of the conversation and message timestamps. Message frequency distribution: a bar chart or histogram showing the distribution of different message types or message lengths within the conversation history. Fine-tune parameters. Batch size: this parameter controls the number of messages processed in each batch during insertion or retrieval operations. A higher batch size can potentially improve performance, but it might also increase memory usage. Max history length: this parameter defines the maximum number of messages to store in the database. This helps manage storage space and ensure that only the most relevant conversations are retained. Uncertainty methods. NA: there are no inherent uncertainty methods associated with this class, as it primarily focuses on storing and retrieving data. However, uncertainty might arise from factors like data corruption, database errors, or connection issues. Challenges and fixes. Challenge 1: connection errors: the connection to the PostgreSQL database might fail due to issues like incorrect connection information, network connectivity problems, or database server downtime. Sample use case that resulted in challenge 1: attempting to access the database with an invalid password or an unreachable database host. Fixes to challenge 1: verify the connection string for accuracy, including the database host, port, username, password, and database name. Ensure that the PostgreSQL server is running and accessible. Troubleshoot network connectivity issues. Challenge 2: data corruption: data integrity might be compromised due to unexpected database errors, data inconsistencies, or external factors like power outages. Sample use case that resulted in challenge 2: a power outage during a data insertion operation might lead to incomplete or corrupted data. Fixes to challenge 2: implement robust error handling mechanisms to catch and recover from database errors. Use database transaction isolation levels to prevent data inconsistencies. Consider using database backup and recovery mechanisms to restore data in case of corruption. Challenge 3: performance bottlenecks: data insertion or retrieval operations might become slow due to large amounts of data, inefficient database queries, or insufficient database resources. Sample use case that resulted in challenge 3: a conversational agent storing a massive volume of chat history, resulting in slow query response times. Fixes to challenge 3: optimize database queries to improve performance. Index relevant columns in the database table. Consider using database caching mechanisms to reduce query latency. Upgrade database hardware or resources if necessary. Langchain Postgres Checkpoint. Description: the Langchain Postgres checkpoint is a method to efficiently store and retrieve the state of a Langchain agent in a PostgreSQL database. This checkpointing mechanism allows for resuming interrupted workflows, loading historical interactions, and managing large amounts of data. Inputs: agent: the Langchain agent whose state needs to be saved. This could be a conversational agent, a data retrieval agent, or any other type of agent built using Langchain. Database connection: a connection object to the PostgreSQL database where the checkpoint data will be stored. This typically includes information like database name, user credentials, and host name. Outputs: checkpoints state: the current state of the agent is saved in the database as a serialized object. This includes the agent's memory, execution history, and any other relevant data. Agent instance: when the checkpoint is loaded, a new instance of the agent is created from the loaded state, allowing the agent to resume its operation from where it left off. Steps: serialization: the agent state is converted into a format that can be stored in the database, e.g., JSON or a custom serialization format. Database storage: the serialized state is then saved to a table in the PostgreSQL database. The table structure is designed to efficiently store the agent state and retrieve it later. Retrieval: when resuming the agent, the saved state is retrieved from the database and deserialized back into a usable form. Agent initialization: a new agent instance is initialized with the retrieved state, allowing the agent to continue its execution from the point it was saved. Metrics: checkpoint size: the size of the serialized agent state stored in the database. This metric helps gauge the storage efficiency of the checkpointing process. Checkpoint time: the time taken to serialize and store the agent state in the database. This metric helps assess the performance of the checkpointing process. Retrieval time: the time taken to retrieve the saved state from the database and initialize a new agent instance. This metric evaluates the speed of loading the agent from the checkpoint. Visualization plots: checkpoint size over time: a plot showing the size of the checkpoints over time, highlighting any trends in data growth. Checkpoint creation retrieval times: a plot showing the time taken to create and retrieve checkpoints, identifying potential performance bottlenecks. Fine-tune parameters. Serialization format: the format used to serialize the agent's state. Different formats can have varying levels of efficiency and compatibility with the database. Database table structure: the structure of the database table where checkpoints are stored can be optimized for different types of queries and retrieval patterns. Compression: using compression techniques for the serialized state can reduce the size of the checkpoints and improve storage efficiency. Uncertainty methods. Database connection reliability: the reliability of the database connection can affect the performance and accuracy of checkpointing. Implementing redundancy or failover mechanisms can mitigate potential connection issues. Data consistency: ensuring data consistency between the agent's internal state and the saved checkpoint is crucial for accurate resumption. Implementing strategies to handle data updates during checkpointing can maintain data consistency. Challenges and fixes. Challenge 1: database connection errors: the process may be interrupted due to errors in connecting to the database, causing data loss or inconsistencies. Sample use case that resulted in challenge 1: an unstable network connection caused a timeout during checkpointing, resulting in the loss of the agent's state. Fixes to challenge 1. Implement retry mechanisms to handle temporary connection errors and use robust error handling to prevent data loss. Consider using connection pooling to improve performance and reduce connection overhead. Challenge 2. Large checkpoint size. Large agent states can lead to bulky checkpoints that impact performance and storage efficiency. Sample use case that resulted in challenge 2. An agent with a complex memory structure and a long execution history generated checkpoints that were too large for efficient storage. Fixes to challenge 2. Utilize compression algorithms to reduce the size of the serialized state. Implement strategies for selectively saving only essential parts of the agent state to minimize checkpoint size. Langchain Postgres Checkpoint Serializer. Description. Explain in detail the Checkpoint Serializer class in Langchain Postgres provides a mechanism for storing and retrieving checkpoints of a Langchain chain state in a PostgreSQL database. This is particularly useful for handling long-running chains or those that require persistence across sessions. Inputs. Input 1. Explain in detail the Checkpoint Serializer class takes as input a chain object, which represents the Langchain chain whose state needs to be checkpointed. Input 2. Explain in detail it also requires a Postgres connection object, which provides a connection to the PostgreSQL database where the checkpoints will be stored. Outputs. Output 1. Explain in detail the primary output of the Checkpoint Serializer is the ability to save the current state of a Langchain chain to the PostgreSQL database. This state can include things like the chain's input, output, intermediate results, and any other relevant information. Output 2. Explain in detail. Conversely, the Checkpoint Serializer can also load a previously saved checkpoint from the database, allowing the chain to resume from where it left off. Steps. Step 1. Explain in detail when called to save a checkpoint. The Checkpoint Serializer serializes the current state of the Langchain chain into a format suitable for storage in PostgreSQL. This typically involves converting the chain's data into a JSON-like structure. Step 2. Explain in detail the serialized checkpoint data is then inserted into a designated table in the PostgreSQL database. The table is designed to store checkpoints, often with fields like the chain's ID, timestamp, and the serialized state data. Metrics. Metric 1. Explain in detail. One key metric is the success rate of checkpoint saving and loading operations. This tracks how reliably the Checkpoint Serializer handles storing and retrieving checkpoint data. Metric 2. Explain in detail. Another relevant metric is the performance of checkpoint operations, measured by the time it takes to save or load a checkpoint. This helps assess the impact of checkpointing on the overall execution time of the Langchain chain. Visualization plots. Visualization plot 1. Explain in detail. A visualization could track the frequency of checkpointing over time, showing how often the chain state is being saved. Visualization plot 2. Explain in detail. Another plot could show the performance of checkpoint operations, comparing save times and load times across different runs. Fine-tune parameters. Parameter 1. Explain in detail. The Checkpoint Serializer class can be configured with parameters that determine how checkpoints are handled. One key parameter is the frequency of checkpointing, controlling how often the chain state is saved. Parameter 2. Explain in detail. Another parameter might be the maximum size of a checkpoint, setting a limit on the amount of data stored in each checkpoint. Uncertainty methods. Uncertainty Method 1. Explain in detail. The checkpoint serializer itself doesn't directly address uncertainty methods, which are typically related to the models or chains being used. However, by persisting the chain state, it enables the use of uncertainty methods that rely on past execution history. Uncertainty Method 2. Explain in detail. For example, a model might store confidence scores in its checkpoints, allowing for uncertainty estimation based on past predictions. Challenges and fixes. Challenge 1. Explain in detail serialization errors. If the chain state contains complex objects or data structures that are not easily serializable, the checkpoint serializer might encounter errors when trying to convert them to a suitable format. A chain using custom objects with methods or complex data structures like nested dictionaries or lists might fail to serialize properly. Implement custom serialization logic for complex objects, potentially using libraries like Pickle or defining custom JSON encoders/decoders. Challenge 2. Explain in detail database connection issues. If there are problems connecting to the PostgreSQL database, checkpoint operations could fail. This might happen due to network issues, database errors, or authentication problems. A chain running in a different environment or with incorrect database credentials might experience connection failures. Ensure the database connection parameters are correctly configured. Handle connection errors gracefully, potentially retrying the connection or logging the errors for debugging. Langchain Postgres Checkpoint Pickle Checkpoint Serializer. Description: the Pickle Checkpoint Serializer allows you to store Langchain checkpoints, which are essentially Python objects in a PostgreSQL database. This is particularly useful for persistence, preserving the state of your Langchain chains and agents across sessions, enabling you to resume from where you left off. Scalability: enabling multiple instances of your application to access and share the same checkpoint data. Inputs: checkpoint data, a Python dictionary containing the data you want to serialize and store in a database. This can be the state of your Langchain chain, agent, or any other relevant information. Table name: the name of the table in your PostgreSQL database where the checkpoint data will be stored. Connection string: a connection string that allows Langchain to connect to your PostgreSQL database. This string should include the necessary information, like host name, port, database name, username, and password. Outputs: checkpointed, a unique identifier, typically an integer assigned to the stored checkpoint data in the PostgreSQL database. Steps: Pickle serialization: the checkpoint data is first serialized using the standard Python Pickle library. This converts the data into a byte stream that can be stored efficiently in the database. Database insertion: the serialized byte stream is then inserted into the specified PostgreSQL table as a new row. Metrics: serialization time measures the time it takes to serialize the checkpoint data. Database insertion time measures the time taken to insert the serialized data into the PostgreSQL table. Visualization plots: checkpoint storage history: a plot that visualizes the timestamps of checkpoint storage events, providing insights into the frequency and timing of checkpoints. Fine-tune parameters: compression optional if you want to reduce the size of the serialized checkpoint data. You can specify a compression method, e.g., gzip, zlib, to compress the byte stream before storing it in the database. Pickle protocol optional: you can specify the Pickle protocol version to use for serialization. This allows you to fine-tune compatibility with different Python versions. Uncertainty methods: this serializer is deterministic and does not introduce uncertainty. Challenges and fixes: Challenge 1 Database connection errors. Sample use case that resulted in challenge 1 connecting to the wrong PostgreSQL database or providing incorrect credentials. Fixes to challenge 1. Ensure that the connection string is accurate and points to the correct database. Verify that the username and password used in the connection string are valid. Check if the PostgreSQL server is running and accessible. Challenge 2 Table name mismatch. Sample use case that resulted in challenge 2 The table name provided in the code does not match the actual table name in the PostgreSQL database. Fixes to challenge 2. Verify that the table name used in your code is identical to the name of the table in the PostgreSQL database. Check for potential typos or discrepancies in the table name. Ensure the table exists in the database. Challenge 3 Data corruption due to incompatible pickle versions. Sample use case that resulted in challenge 3 attempting to load a checkpoint that was serialized using a different pickle protocol version than the one used during loading. Fixes to challenge 3. Use the same pickle protocol version for both serialization and loading to avoid compatibility issues. If you need to load a checkpoint serialized with a different protocol version, consider upgrading or downgrading the pickle library in your environment to ensure compatibility. Langchain Postgres Checkpoint Postgres Saver. Description: The Postgres Saver checkpoint in Langchain is a tool for storing and retrieving your chain state in a PostgreSQL database. This is particularly useful for applications that require persistent storage, allowing you to resume your chain's execution after interruptions or continue where you left off. Inputs: Connection string. The connection string for your PostgreSQL database. This string contains the necessary information to establish a connection to your database, including host, port, database name, username, and password. Table name: the name of the table within your PostgreSQL database where the checkpoints will be stored. Runed: an identifier to uniquely identify each run of your Langchain application. This is helpful for distinguishing different runs within the same database table and for tracking their progress individually. Chain: the Langchain chain whose state you wish to save or load. Outputs: Saved checkpoint. The checkpoint information is stored as a row in the specified table within the PostgreSQL database. Loaded checkpoint. The checkpoint information is retrieved from the database and used to restore the state of the Langchain chain. Steps: Establish database connection. The Postgres Saver establishes a connection to your PostgreSQL database using the provided connection string. Save checkpoint. Optional if you are saving a checkpoint. The Postgres Saver serializes the current state of the chain including memory, history, etc., and stores this information as a new row in the specified table. Load checkpoint. Optional if you are loading a checkpoint. The Postgres Saver retrieves the checkpoint data from the table using the runed as a key. The data is then used to rehydrate the chain, restoring its state to the point where it was last saved. Metrics: Checkpoint size. The size of the serialized checkpoint data in bytes. Checkpoint save time. The time taken to save the checkpoint data to the database. Checkpoint load time. The time taken to retrieve the checkpoint data from the database and rehydrate the chain. Visualization plots: Checkpoint time series. A line graph that plots the checkpoint save times over time. Checkpoint size distribution. A histogram that shows the distribution of checkpoint sizes over time. Fine-tune parameters: Serialization method. The method used to serialize the chain state. You can choose between different serialization methods like JSON or pickle. Compression method. The method used to compress the serialized data before saving it to the database. This can help reduce storage space. Uncertainty methods. None. The Postgres server itself doesn't introduce uncertainty, but it relies on the serialization method for the chain state, which may introduce uncertainty depending on the chosen method. Challenges and fixes. Challenge 1. Database connection errors. If the connection string is incorrect or the database is not accessible, the Postgres server will fail to establish a connection, leading to errors in saving and loading checkpoints. Sample use case. A user misconfigures the connection string, providing the wrong database name. Fixes. Verify the connection string and ensure that it is correct. Confirm that the PostgreSQL server is running and accessible. Check the database credentials, username and password provided in the connection string. Challenge 2. Table schema mismatch. If the table structure in your PostgreSQL database does not match the expected schema for storing checkpoints, you will encounter errors during checkpoint operations. Sample use case. The table is created with a different set of columns than required by the Postgres server. Fixes. Ensure that the table schema matches the required columns for checkpoint storage. Create the table correctly using the necessary column types and names. Challenge 3. Serialization errors. If the chosen serialization method is not compatible with the chain state or if there are issues with the serialization process, errors can occur. Sample use case. The chain includes a custom object that is not serializable using the chosen method. Fixes. Choose a serialization method that supports the types and structures in the chain state. Address any errors or inconsistencies during serialization. Consider using a custom serialization method if necessary. Challenge 4. Large checkpoint sizes. If the checkpoint data becomes very large due to the chain's complexity or memory usage, it can lead to performance issues and database storage constraints. Sample use case. A chain maintains a large history of previous interactions, resulting in significant checkpoint size. Fixes. Optimize the chain's memory management to reduce the amount of data stored in the checkpoint. Consider using compression to reduce the size of the checkpoint data. Implement a strategy to limit the history size or periodically discard old data. Challenge 5. Concurrency issues in a multi-user environment. If multiple users attempt to save or load checkpoints simultaneously, concurrency issues can arise. Sample use case. 2 users running the same Langchain application attempt to save checkpoints to the same table concurrently. Fixes. Implement locking mechanisms in your database to prevent simultaneous access to the same table. Use transactions to ensure atomic checkpoint operations. Consider using separate tables or database instances for different users or runs. Langchain Postgres Vector Stores. Description. Explain in detail. The Langchain PostgreSQL Vector Store is a vector database that utilizes PostgreSQL to store and retrieve vector embeddings. It offers a powerful and scalable solution for storing and querying large amounts of data embedded in vector space. Inputs. Input 1. Explain in detail a list of text documents to be embedded and stored. The documents can be in various formats, such as strings, files, or URLs. Input 2. Explain in detail a PostgreSQL database connection object or connection details used to establish the connection to the database. Outputs. Output 1. Explain in detail a vector store object that represents the embedded data stored in the PostgreSQL database. The object provides methods for adding new documents, retrieving documents based on similarity searches, and querying the database. Output 2. Explain in detail vector embeddings for each document in the input list. These embeddings are stored in the PostgreSQL database in a dedicated table, allowing for efficient similarity searches. Steps. Step 1. Explain in detail initialization. The Langchain PostgreSQL vector store is initialized with a connection to a PostgreSQL database. The connection object or details are passed to the constructor. Step 2. Explain in detail embedding in storage. The input documents are embedded using a chosen embedding model. The embeddings are then stored in the PostgreSQL database in a dedicated table. The table schema typically includes columns for the document ID, the embedded vector, and other relevant information. Metrics. Metric 1. Explain in detail similarity search accuracy measures the accuracy of the vector search in finding relevant documents based on a query vector. Metric 2. Explain in detail retrieval speed measures the time it takes to retrieve documents based on a query vector. Visualization plots. Visualization plot 1. Explain in detail vector similarity plots. These plots visualize the similarity relationships between documents in the vector space, providing insights into the clusters and relationships within the data. Visualization plot 2. Explain in detail retrieval accuracy plots. These plots show the accuracy of the vector search for different query vectors, allowing for evaluation of the effectiveness of the vector store. Fine-tune parameters. Parameter 1. Explain in detail embedding model. Choosing a suitable embedding model based on the nature of the data and the search requirements. Parameter 2. Explain in detail similarity metric. Selecting an appropriate similarity metric for comparing vectors, such as cosine similarity or Euclidean distance. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. The vector store can provide confidence scores for retrieved documents, indicating the level of certainty about the similarity. Uncertainty method 2. Explain in detail nearest neighbors. The vector store can return a list of nearest neighbors for a query vector, allowing for exploration of similar documents with varying degrees of similarity. Challenges and fixes. Challenge 1. Explain in detail data size limitations. Large-scale data storage and retrieval can be challenging in PostgreSQL databases, potentially leading to performance issues or database size constraints. Sample use case that resulted in challenge 1. Attempting to store a large corpus of text documents, exceeding the storage capacity of the PostgreSQL database. Fixes to challenge 1. Utilize PostgreSQL's sharding and partitioning features to distribute data across multiple databases or tables. Optimize data storage efficiency by using compression techniques for the embeddings and other data. Consider using specialized database systems designed for vector search, such as FIS or Milvus, for large-scale data management. Challenge 2. Explain in detail performance limitations. Retrieving vectors based on similarity searches can be computationally intensive, leading to performance bottlenecks, especially for large datasets. Sample use case that resulted in challenge 2. Performing similarity searches on a large dataset with millions of embedded documents, resulting in slow query response times. Fixes to challenge 2. Optimize query execution plans using PostgreSQL's Query Optimizer, ensuring efficient index utilization and data access. Utilize vector search indexes, such as ANOI or HNSW, for accelerating similarity searches. Explore distributed vector search systems, such as Elasticsearch or Pinecone, for handling large datasets with high performance requirements. Langchain Postgres Vector Stores Distance Strategy. Description: the distance strategy parameter in Langchain's Postgres vector stores allows you to choose the method used for calculating similarity between vectors. This determines how the vector store finds the most relevant results based on your query inputs. Query vector. This is the vector representation of the search query you provide. Database vectors. These are the vectors stored in the Postgres database, representing the data points, documents, sentences, etc. you want to search within. Outputs. Similarity scores. The distance strategy produces similarity scores for each database vector compared to the query vector. Ranked results. The database vectors are then ranked based on their similarity scores, providing the most relevant results first. Steps. Vector calculation. Both the query vector and the database vectors are embedded using a chosen embedding model. Distance calculation. The chosen distance strategy is applied to calculate the distance or similarity between the query vector and each database vector. Metrics. Retrieval accuracy measures how well the vector store retrieves the most relevant documents based on the query. Retrieval efficiency measures the speed at which the vector store performs searches. Visualization plots. Similarity score distribution. A plot showing the distribution of similarity scores for all database vectors compared to the query vector. Fine-tune parameters. Non-distance strategies are typically not fine-tuned within Langchain's Postgres vector stores. Uncertainty methods. Non-distance strategies themselves don't directly address uncertainty, though the choice of strategy can impact the confidence of retrieved results. Challenges and fixes. Challenge 1. Choosing the right distance strategy for your specific data and search use case. Sample use case that resulted in challenge 1. Using cosine similarity for text search when data exhibits a strong semantic relationship might be less effective than using Euclidean distance. Fixes to challenge 1. Experiment with different distance strategies, cosine similarity, Euclidean distance, etc. to identify the best one for your data. Consult the documentation of the chosen embedding model for guidance on recommended distance strategies. Challenge 2. Handling high dimensionality in vector spaces. Sample use case that resulted in challenge 2. Working with very large vectors can lead to computational inefficiency and potential issues with distance calculation. Fixes to challenge 2. Consider using dimensionality reduction techniques, e.g., PCA, before storing vectors in the database to reduce the computational burden. Explore approximate nearest neighbor and search techniques that can efficiently find similar vectors in high-dimensional spaces. Langchain Postgres Vector Stores PG Vector. Description: PG Vector is a Langchain vector store designed for storing and querying vector embeddings within a PostgreSQL database. It leverages the PostgreSQL extension PG Vector to efficiently store and perform similarity searches on vector data. This integration allows you to benefit from PostgreSQL's robust data management capabilities and scalability while leveraging vector similarity search for applications like semantic search, recommendation systems, and question answering. Inputs. Connection details for the PostgreSQL database. This includes the host, port, database name, username, and password needed to establish a connection. Table name: the name of the PostgreSQL table where you want to store the vector embeddings. Embedding function: this is a function that takes a text input and generates a numerical vector representation. Langchain provides pre-built embedding functions like OpenAI embeddings, Hugging Face embeddings, etc. Or you can define your own custom embedding function. Data: the data you want to store in the vector store. This can be a list of documents, a pandas data frame, or any other structure that can be processed by the provided embedding function. Dimensionality of the vectors, the number of dimensions in each vector, e.g. 1536 for OpenAI's text embedding ADA002 model. Optional parameters. Index name, the name of the GIN index to create on the vector column. Distance metric, the distance metric to use for similarity search, e.g. cosine. Euclidean. Upset and conflict, the Boolean flag that determines whether to insert new data or update existing data if there are duplicate entries in the table. Outputs. Vector store object, this object provides methods for adding new data, searching for similar vectors, and retrieving vectors based on their identifiers. PostgreSQL table containing vector data, the vector embeddings are stored as a column in the specified PostgreSQL table. Steps. Establish a connection to the PostgreSQL database using the provided connection details. Check if the specified table exists. If not, create it with a column to store the vector embeddings using the pgvector extension. Create a GIN index on the vector column, optional. Embed the input data using the provided embedding function. Insert the vector embeddings and corresponding metadata into the PostgreSQL table. Return a vector store object that encapsulates the connection to the database and provides methods for interacting with the vector data. Metrics. Similarity search performance measured by the time it takes to perform a similarity search query. Storage efficiency evaluated based on the amount of storage space required to store the vector embeddings. Index performance, the efficiency of the GIN index in speeding up similarity searches. Visualization plots. Distribution of vector embeddings. This plot shows the distribution of vectors in the embedding space, revealing potential clusters or outliers. Nearest neighbors search results, a visualization of the retrieved nearest neighbors for a given query vector. Fine-tune parameters. Embedding model, experiment with different embedding models to find the one that best captures the semantic relationships in your data. Distance metric. Choose the distance metric that best suits the characteristics of your data and the nature of the similarity search you want to perform. Index configuration. Optimize the GIN index parameters, e.g. index strategy. Size of the index to improve search efficiency. Uncertainty methods. Confidence scores. Calculate confidence scores for retrieved results based on the similarity scores or distance metrics. Ensemble methods combine multiple embedding models or distance metrics to provide more robust similarity search results. Challenges and fixes. Challenge 1. Scalability issues for large datasets. Storing and searching through a large number of vectors in PostgreSQL can become slow. Sample use case that resulted in challenge 1. A large e-commerce platform with millions of product descriptions needing to be indexed for semantic search. Fixes to challenge 1. Utilize specialized vector database systems like Pinecone, Milvus, Viviate for high-performance vector storage and search. Explore techniques like sharding or partitioning the data in PostgreSQL to distribute the workload. Consider leveraging cloud-based PostgreSQL services, e.g. Amazon RDS, Google Cloud SQL for more scalable storage and compute resources. Challenge 2. Maintaining data consistency. Ensuring that the vector data in the database is kept synchronized with changes in the source data can be challenging. Sample use case that resulted in challenge 2. A knowledge base with frequently updated documents, where the vector representations need to be refreshed regularly. Fixes to challenge 2. Implement a data pipeline or trigger mechanism that automatically updates the vector embeddings whenever the source data changes. Use a combination of PostgreSQL's triggers and materialized views to maintain consistency between the raw data and the embedded vectors. Challenge 3: limited support for advanced search functionalities. PostgreSQL's native vector search capabilities might not always support complex search scenarios like range queries or nearest neighbor search with multiple constraints. Sample use case that resulted in Challenge 3: a recommendation engine needing to filter recommendations based on specific attributes or ranges of values in addition to semantic similarity. Fixes to Challenge 3: extend the queries with additional filtering clauses or joins based on other relevant columns in the database table. Investigate whether the PG vector extension provides more advanced search options or explore other PostgreSQL extensions that might better support the desired search functionality. Explore specialized vector database systems that offer more advanced query capabilities.